Hello, everybody. This is my lecture for week 14, session 1. So in this chapter, we'll go over the gas power cycle. Some of you guys asked me about this, picture. What's the relationship between this picture, this actual, car, and, the thermodynamics. So in this chapter, actually, we will go over, the auto cycles, which is actually provide or generate energy for cars by using the auto cycle. So what we are going to do in this chapter, we actually try to use all previous chapters to design auto cycles and diesel cycles. So we'll use the uh, actually energy balance for cycles. We'll use the energy balance for closed system, for open system, to just analyze the gas power cycles. So yeah, as an the main objective of this chapter, first I will go over some definitions, some basic concept of gas power cycles, and then we just discuss auto cycle and diesel cycles. So in intermediate thermofluids, you will learn about the Brighton cycles, Brighton cycles with regeneration, jet propulsion cycles, and other cycles. So in this actually course in Thermo 1, we just go over the diesel cycle and auto cycle, and also some basic concept of gas power cycles. So today I just go over, I will go over some, definitions, some concepts. So it's a kind of introduction for chapter 9, and then hopefully next lecture we'll go over the auto cycles, and then I solve one problem, and then we can go over the diesel cycle and concept of diesel cycle. So keeping in mind that most power producing devices operate on cycles, in chapter 6, we discussed the heat engines. If you remember, in heat engines, actually heat is provided to the system and the desired output is W. So you already learned, one of the actually power producing, devices. So keeping in mind that normally the power cycles can be gas cycles or vapor cycles. In gas cycles, we are dealing with just one phase, gas phase. In vapor cycles, we are dealing with the two phases, meaning that the working fluid is in vapor in part of this cycle and is in liquid form in another part of the cycle. So we have the phase change in the vapor cycle. So in gas cycles there is no actually phase change. In vapor cycles there is a phase change. If you remember, the heat engine is a vapor cycle, because we had actually phase change in the heat exchanger. So what's the benefit of phase change? If you want to actually transfer a huge amount of heat, you should use the vapor cycle. So we already discussed that we have two types of heat actually transfer: the latent heat and also sensible heat. So for the sensible heat, the temperature changes. However, for the latent heat, the temperature is constant, but the phase of substance changes from, for example, liquid to vapor, from vapor to liquid. So the difference between these two actually, a cycle, is that normally in the vapor cycle, we can transfer a huge amount of, heat by using the vapor cycles. So in addition to this, classification, thermodynamic cycles can be open or closed. In this chapter, we actually concentrate on the various gas power cycles. In the next chapter, hopefully in the intermediate thermofluids, next semester, you will learn about the vapor cycles. But in this chapter, we concentrate on the various gas power cycles. And again, in this course, Thermo 1, we just concentrate on auto cycles and diesel cycles. So in chapter 6, you learn about the ideal cycles. We discussed the Carnot cycles, and then you learn that by actually defining these ideal cycles, for example, the Carnot cycle, we can actually define a maximum value for the efficiency, and also it's much easier to analyze the for example Carnot cycle. So we can just remove the reversibilities, and then it's much easier to actually analyze this type of cycles. So in this chapter we define ideal cycle. So what is the ideal cycle? The ideal cycle is a cycle which is close to the real cycle, and it's internally reversible process. Correct? Internally reversible process. Keep in your mind that in actually ideal cycle, we use some assumption. The first assumption is that we assume that working fluid is always in the gas actually state. So there is no phase change. So keep in your mind that the ideal cycle is different from the Carnot cycle. The Carnot cycle is the cycle which is both internally and externally reversible. However, the ideal cycle is internally reversible. So meaning that it can be externally reversible or irreversible. So ideal cycle is internally reversible. The Carnot cycle is both internally and externally reversible. This is the difference between the ideal and Carnot cycle. In ideal cycle, we assume that there is no friction, and so we assume that all expansion, all compression occurs, in a quasi-equilibrium manner, and also we assume that all kinetic and potential energy changes of working fluid is negligible. So you can cancel the terms for kinetic and potential energy in first thermodynamic law or energy balance equation. So okay, so yeah, as we discussed, guys, the actual cycles, we have three types of, cycles. So we have the actual cycles, we may have the ideal cycles, and auto cycles. So for actual cycles, you need to consider both internal and external, irreversibilities. For ideal cycles, they are internally reversible, and the Carnot cycles, they are both internally and externally reversible. So actual cycles, ideal cycles, and Carnot cycle. So if you remember, we already discussed the definition of thermal efficiency of heat engines, or the general definition for efficiency. The definition for efficiency is desired output over required input. So for a heat engine, if you remember from chapter 6, the desired output is W out and the required input is QH. So, or Q in. By using the definition for, or you can just write it, based on the unit mass, both W and Q. So, just think about the relationship between the efficiency of actual cycle, ideal cycle, and Carnot cycle. Based on this definition for the ideal cycle, for actual cycle, and for Carnot cycles, what do you think about the thermal efficiency of a heat engine? I mean actual heat engine, ideal heat engine, and Carnot heat engine. Please pause this video, think 2 minutes. What do you think? What's the relationship between the thermal efficiency of these three different heat engine cycles? So, yeah, based on the definition, because Carnot cycle is both internally and externally reversible, it must have the highest thermal efficiency. So Carnot actually thermal efficiency is the highest one. After that, because the ideal one is internally reversible, it has higher thermal efficiency than the actual one. However, its thermal efficiency is lower or equals to the Carnot cycle. So here, this is the relationship between, the thermal efficiency of actual, ideal, and Carnot heat engine based on, their definition. So if you remember from the previous chapters, the actually area under the PNU diagram or equals to the work, and the area under the TS diagram equals to the heat. So for a cycle, the area enclosed by the cycle equals to W net on the PNU diagram, and the area enclosed by the TS diagram equals to the Q net. So keep in your mind that for these cycles, if you write the first thermodynamic law, you can show that the Q net equals to W net, meaning that the area enclosed by the TS diagram of gas power cycles should be equals to the area enclosed, by the PNU diagram of the, this gas power cycle. So meaning that this area here equals to the, this area, enclosed, by the gas power cycle TS diagram. So meaning that, the area enclosed on the, by the PNU diagram of gas power cycle equals to W net, and then this is equals to Q net. So and then eventually this area equals to this area. So before we start, the gas power cycle, it's a good idea if we just go over the Carnot heat engine cycle. If you remember from chapter 6, each and every Carnot heat engine cycle includes 4, totally reversible process. It has 2 actually isothermal steps and 2 isentropic steps. First, for the process between point 1 and point 2, Q is added to the system in an isothermal process. Then the fluid is expanded, in actually isentropic expansion. Then at constant temperature, heat is rejected to the surrounding, and then eventually there is an isentropic compression, steps for the Carnot heat engines. So the Carnot efficiency, you can again write the W actually net over the Q in, or by using the temperatures, you can write the thermal efficiency for the Carnot cycle equals the 1 minus TL over TH. Keep in your mind that this temperature must be absolute temperatures. Don't use centigrade, don't use Fahrenheit, to calculate the thermal efficiency of Carnot cycle. So if you want to calculate the thermal efficiency of a Carnot cycle, you must use the absolute temperature to calculate the thermal efficiency. And then this is the TS diagram, for Carnot heat engine. So it has 2 actually constant temperature or isothermal steps and 2 isentropic steps. And then keep in your mind that this area here equals to this area enclosed by the PNU diagram, because you can write for these cycles or any other cycle, Q net equals to W net. Now, question. We are interested in increasing the thermal efficiency of heat engines, the Carnot heat engine, the ideal heat engine, or the actual one. Why we are interested? Because the higher thermal efficiency, keep in your mind that what was the definition of thermal efficiency? The thermal efficiency is desired output, which is W here. So the higher thermal efficiency means the higher work, the higher W, correct, from the system. So we are interested in the higher, thermal efficiency. Based on this equation, if you want to increase the thermal efficiency of a Carnot, heat engine or an ideal one, so what you need to do, you need to decrease this term, correct? So to decrease this term, you can decrease the TL temperature or increase the TH. So these are actually 2 methods to increase the thermal efficiency of heat engines. By increasing the temperature, from the actually the temperature of the source that provide heat to the system, or by decreasing the temperature of the sink or source, that heat is rejected to that actually sink. So these are two actually methods to increase the thermal efficiency of ideal, actual, and Carnot heat engines. So we already discussed that this area should be equals to this area. So this is actually a short review from the previous section, previous lectures, previous chapters. In this chapter, guys, we actually need to use the air standard assumption. What is the air standard assumption? The air standard assumption is a cycle, or a standard cycle is a cycle that use air as a working fluid, and also we use the standard, actually air standard assumption. What is the air standard assumption? What is the air standard cycle? And also, what is the application of these air standard cycles? Let's go back, yeah, 2, 3 slides. Look, guys, here for each and every heat engine, Q should be provided to the system, correct? So normally this Q is supplied by using a combustion chamber, correct? So for each and every actually heat engine, we need to have a combustion chamber here to supply heat to the cycle. So we need to have a combustion chamber. So this combustion chamber, to analyze this combustion chamber here, we need to use the air standard assumption. What is the air standard assumption? What is the air standard cycle? Let's go over this standard air standard cycle. So again, guys, what is the application of this cycle? We have a step here, to actually supply heat to the system. So this actually step is this step includes a combustion chamber. So we need to analyze this combustion chamber. Keep in your mind that, guys, you will learn about the combustion equation, combustion chambers, I think in chapter 15, in the intermediate thermal fluids. Keep in your mind that normally combustion process are complex processes. In chemical engineering, normally we actually need to spend a semester to learn about the combustion process, the combustion reaction. So in this actually course, we can use the standard air standard cycle to simplify that process. So in this actually assumption, first we assume that heat, actually air, is the main working fluid of the combustion chamber. So we cancel the fuel. We just assume that we have the air. What is the application of this assumption? The application is that to actually calculate Q here, you just need to use the thermophysical properties of air. If you assume that you have both air and fuel here, then what you need to do, you need to just consider both to fuel and air thermophysical properties. For example, to calculate the CP, you need to consider both air and fuel CP. And then it's a little bit complex. You need to have the information about the air fuel ratio. You need to have temperature, pressure. So you can actually simply assume that air is the only working fluid. Now, question: is it a good assumption? Does it make sense to cancel the fuel? So if you check the actually air fuel ratio for different cars, automobiles, you will see that this ratio, this air fuel ratio, is normally more than 12. In some cases the air fuel ratio is more than 16. Just Google it right now about your car, and then just check the air fuel ratio in your car here, actually engine. And then you will see that in most cases this ratio, air to fuel, actually more than 90% of this mixture is air. So it makes sense to just assume that we have air in the inlet, correct? So it's a reasonable assumption to just cancel the fuel, and then we assume that we have air, and then you can use the thermophysical properties of air. This is the first thing. The other thing is that, okay, if you have air, there is no combustion chamber. So what is the source, for the heat actually, uh, for the heat, in this combustion chamber? We assume that there is external resource to just supply heat to this system. So, and then by having, the information for the, energy released by the, air fuel combustion, reaction, we can actually get some idea about this heat. So this is, some basic assumption for air standard cycle. The first thing is that we assume that the working fluid is air. We cancel the fuel, correct? The second one, we assume that this air actually is an ideal gas, meaning that you can use the ideal gas equation of state to calculate, the property of this air. We assume that all process actually take place, under the internally reversible processes. And then we just cancel this combustion chamber. We assume that, there is a heat addition process to supply heat to this, process. And then this is, the basic concept of the air standard cycle, correct? Air standard cycle, the working fluid is air, and then we use this assumption. In some cases, you may see this cold air standard assumption. If you see this statement, for example, use the cold air standard assumption, you need to assume that the air is at room temperature, and then use the CP or other thermophysical property of air at 25 degree centigrade, correct? So if you have this air, statement, for example, use the cold air standard assumption, just use the CP of, constant CP of air at 25 degree centigrade for the, calculations. Okay. So now we can, gradually start, the main topic of this, chapter, reciprocating engines. What is the reciprocating engine? Normally, if you check, your car engine, we have a, piston and cylinder, and then in this piston and cylinder, air and fuel are, provided, and then, there's a combustion, actually, reaction here, and then there's intake valve, SX house valve, and then we can just generate W shaft here, correct? So look, guys, we can use the air standard assumption here. We can assume that the actually only fluid here is air, and then Q is supply, from the external resources, and then we can actually analyze, the a gas power cycle. So to analyze this actually gas power cycle, we need to just go over some, definition. We have two definition, for the TDC, top dead center, and bottom dead center. The TDC is, the actually point where the piston is at its minimum, position. The BDC is the place where this actually piston is in its maximum, position. The distance between the TDC and BDC is called a stroke. So based on this definition, we may have two stroke, cycles, or four stroke cycles. For the two stroke cycles, this piston moves, in each cycle twice. For the four actually strokes, this piston moves, 4 times, correct? So stroke, the difference between the BDC and TDC. What is the bore? Bore is the diameter of this piston or cylinder. So there is some intake valves to add air and fuel. In this course, we assume we have just air, and exhaust valve, to just remove the combustion product. Also, we have the clearance volume. The clearance volume is the volume where, the piston is at the TDC position. This volume is called clearance volume. The displacement volume is the volume actually between the TDC and BDC. This volume is called, the displacement volume. Here you can see, the displacement volume. Compression ratio. Compression ratio is the Vmax over Vmin. We will discuss in the next, slide. And also the mean effective pressure. Now, this is actually the general concept, for reciprocating engines. Here, to start the combustion reaction, we need to have heat. We need to supply heat to start, this, combustion reaction. Based on the source of heat for this, combustion, to start this combustion, reaction, we may have spark ignition engines or SI engines and compression ignition engines. In the spark ignition engines, this heat actually is supplied by a spark plug. So there's a spark plug here to just supply heat and then to start the combustion reaction. So an example for this spark ignition engine is Otto cycle. So for the compression ignition, there is no spark plug. So heat is supplied by actually we compress this air fuel to increase the temperature of the this mixture to start the combustion reaction. So there is no spark plug, so we just compress the gas mixture, and then that when we just increase the pressure, temperature increases, and then when the temperature goes beyond the ignition temperature of this mixture, the combustion reaction starts. So example for compression ignition engines is diesel cycle, and in this course we will go over both Otto cycle and diesel cycle. So what is the R compression ratio? Keep in your mind that the compression ratio is the ratio of the Vmax over Vmin. The Vmax over Vmin. So the compression ratio is unitless. There is no unit, for the compression ratio. And then the other thing is that the compression ratio is the ratio of to volume. It's not the ratio of to pressure. This is a very common mistake, guys. The compression ratio is the ratio of to volume, but not pressure. It's the ratio of the Vmax over Vmin. So the other thing is that the mean effective pressure. What is the mean effective pressure? The first thing is that it's the fictitious pressure. So look, guys, assume that we have a cycle, for example, this cylinder piston, and then this is the PNU diagram, for this actually, device. So the volume changes between the BDC position and the TDC position. So at the TDC position, we have the Vmin, and in the BDC position, we have the Vmax. At the Vmax, we have the minimum pressure. When this actual piston is at this position, we have the minimum pressure. When this actual piston moves to the TDC, we have the maximum pressure, correct, of the system. So as you can see, the pressure is not constant. The pressure changes. Now we can define a fictitious pressure. This pressure is a constant value. Look, the MEP, mean effective pressure, is the constant pressure. So how we can define this pressure? We can define this pressure in order to make the same area under the MEP line with the W net. Correct? So the MEP is a fictitious pressure that produces the same amount of network as that produced during the actual cycle. Correct? So this is the fictitious constant pressure, and then the area under this curve equals to the W net. This area equals, by the PNU diagram. Correct? So based on the definition, now you can calculate the MEP. correct? This is a rectangle. Based on the definition, you know that the area equals under the P nu diagram is the W net. So this area here equals the W net. This is the rectangle, so you can write the area here equals to the MEP, correct? This side, this pressure times the Vmax minus Vmin. And then from here, you can write the MEP equals the W net over Vmax minus Vmin, or you can write it based on the unit mass. This is the definition for the MEP. What is the application of the mean effective pressure? We can use the mean effective pressure to actually compare the performance of, reciprocating engines with equal sizes. So if you have, for example, two reciprocating engine with the same size and then with different MEP, it actually should select that reciprocating engine with the higher MEP, because the higher MEP means the higher W net, correct? And then this is the actually desired output of this reciprocating engine or this system. So again, MEP can be used to compare the some reciprocating engines with the same size, and then keep in your mind that the higher MEP is actually more desirable. And then eventually, as the last part of this, lecture, keep in your mind that we may have 4 stroke cycle. For the 4 stroke cycle, each cycle includes 4 stroke and 2 revolution, or we may have 2 stroke cycle. 2 stroke cycle includes 2 stroke and 1 revolution per cycle. So normally the 4 stroke cycle are more efficient. However, the 2 stroke cycles are cheaper, they are simpler. So for some application, for example, such as motorcycles, you can use the 2 stroke cycles. So please go over this definition, guys. These are the basic definition for this chapter. We will use this concept, this definition in the next lecture when I introduce the auto cycle, and then you will see that we will use all this definition, this concept to just analyze the auto cycle. Thank you so much and have a great day.